You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Code generation systems are artificial intelligence applications designed to produce source code in programming languages based on natural language instructions or structured prompts. These systems build on the same foundations as large language models for text, but are adapted to handle the syntactic and semantic rigor of programming. Where ordinary text models focus on language fluency, code models must adhere to precise rules, since a missing bracket or misplaced keyword can break functionality. The central idea is to bridge human intent with machine executable logic, enabling non-experts to express goals in natural language and developers to accelerate their workflows with intelligent suggestions. Code generation systems do not eliminate the need for human programmers but extend their capacity, automating routine tasks and allowing engineers to focus on higher-level design, architecture, and problem-solving. In this sense, they act less as replacements and more as collaborators, augmenting human creativity and precision. The role of these systems in software development has grown steadily as their accuracy and reliability improve. Developers often face repetitive coding tasks, writing boilerplate, configuring integrations, or implementing patterns that follow predictable structures. Code generation systems can automate these tasks, freeing time for more complex challenges. They also assist during live development, offering autocomplete suggestions, generating documentation, or providing code snippets tailored to the current project context. For example, a developer building an API might ask the system to scaffold endpoint handlers, saving hours of manual setup. By accelerating low-level coding and reducing context switching, these tools integrate into the developer's workflow, providing continuous support. They are not a replacement for expertise, but rather an extension of it, functioning as intelligent assistants embedded within the development cycle. Model architectures for code are specialized adaptations of large language models. Standard models are trained on diverse text corpora, but code-focused models are further pre-trained on massive collections of programming repositories, ensuring familiarity with syntax, patterns, and idioms. These models learn to map input prompts, whether natural language descriptions or partial code snippets, to valid code completions. Transformer architectures dominate this field, with their ability to capture long-range dependencies, making them well-suited for programming tasks where relationships may span multiple functions or files. Beyond basic prediction, advanced models attempt to embed semantic reasoning, ensuring not only that generated code compiles but that it matches the intent described. Architectural refinements, such as incorporating abstract syntax trees, further enhance the model's ability to generate structured, logical outputs that align with programming norms. Datasets play a pivotal role in shaping the capabilities of code models. Public repositories such as GitHub provide vast amounts of open-source code that capture real-world practices across languages and frameworks. Documentation, tutorials, and Q&A platforms add natural language explanations, linking programming concepts with their implementations. Synthetic datasets, generated through programmatic templates, supplement these sources by creating controlled examples for specific tasks like function completion or bug fixing. While the abundance of data strengthens model performance, it also introduces concerns about quality, license compliance, and bias. Poorly written or insecure code in training datasets may propagate into model outputs, while reliance on permissively licensed code risks obscuring intellectual property boundaries. Dataset design is therefore both a technical and ethical challenge, shaping not only what models can do, but how responsibly they do it. The strengths of code generation systems are most apparent in areas where patterns dominate. Autocomplete features accelerate typing by predicting function names, parameters, and common idioms. Generating boilerplate code, such as class structures or configuration files, reduces drudgery. Systems excel at filling in repetitive logic where creativity is minimal but accuracy is essential. For example, creating data access layers or unit test scaffolds is often formulaic, making it an ideal application for automated generation. These strengths highlight the collaborative nature of code models. They shine where predictability and repetition align with model training, leaving humans free to focus on design, strategy, and innovation. By combining human oversight with machine efficiency, productivity is amplified while risk is contained. Limitations, however, remain significant. Models may generate insecure code by defaulting to unsafe patterns learned from training data. They may suggest inefficient algorithms, fail to handle edge cases, or introduce subtle logical errors that compile correctly but behave incorrectly at runtime. Unlike human developers, AI lacks genuine understanding of context, goals, or trade-offs, relying instead on statistical correlations. This can lead to outputs that appear correct on the surface but harbor hidden flaws. Moreover, code models often lack awareness of evolving best practices or security standards, meaning their outputs can quickly become outdated. These limitations underscore the need for human oversight, rigorous testing, and integration with existing software quality practices. Blind reliance on generated code risks introducing vulnerabilities or inefficiencies at scale. Testing is therefore a cornerstone of responsible code generation. Generated outputs must be validated against unit tests or broader test suites to ensure correctness and reliability. Automated testing frameworks provide immediate feedback, identifying whether code meets functional requirements. For example, if a generated function is supposed to calculate compound interest, test cases can verify its accuracy under a range of scenarios. Code models themselves can even generate candidate test cases, though these too require validation. Testing closes the loop between generation and verification, ensuring that AI-assisted development remains grounded in functional correctness. Without robust testing, confidence in generated code is misplaced, since syntactic validity alone does not guarantee correctness. Static analysis provides another line of defense by inspecting generated code without executing it. These tools analyze code structure, data flow, and control paths to detect potential bugs, vulnerabilities, or inefficiencies. For example, static analysis can flag unused variables, unhandled exceptions, or unsafe memory operations. Security-focused tools highlight risks like SQL injection or buffer overflows. Integrating static analysis into the pipeline ensures that generated code undergoes scrutiny before deployment, catching issues early, and reducing the likelihood of vulnerabilities reaching production. Static analysis complements testing by identifying problems that may not be revealed by specific test cases, providing broader coverage and reinforcing code safety. Repair loops represent an iterative approach to refining code generation. Instead of treating the model's first attempt as final, repair loops use test results and static analysis feedback to guide successive refinements. If tests fail, the model can be prompted to fix the issues, repeating until outputs pass. This mimics how human developers debug and iterate, gradually improving code quality. Repair loops transform generation into a process of continuous improvement, increasing reliability. For example, an AI assistant might generate an initial implementation of a function, run the associated test suite, detect a failure, and revise its approach until the function passes all cases. By automating this cycle, repair loops push models closer to autonomous development, though human oversight remains critical to ensure alignment with design intent and broader project goals. Evaluation metrics allow organizations to measure performance systematically. A common measure is pass at K, which evaluates how often at least one of K-generated outputs successfully passes tests. This acknowledges that models often generate multiple possible solutions, some of which may be correct. Additional metrics track compilation success rates, runtime efficiency, or adherence to style guidelines. Benchmarks ensure transparency, allowing comparisons across systems and tracking progress over time. However, metrics must be chosen carefully since superficial measures can obscure real-world utility. For example, code that passes narrow test cases but fails in broader contexts should not be considered reliable. Evaluation frameworks thus serve as both accountability tools and drivers of innovation, ensuring that progress in code generation translates into meaningful, trustworthy outcomes. Applications in industry illustrate the transformative potential of these systems. Developer assistants embedded in integrated development environments provide real-time suggestions, reducing cognitive load and speeding up workflows. Automated documentation tools generate comments or usage examples, improving maintainability. API integration helpers suggest code snippets for connecting to services, accelerating development cycles. By embedding AI into everyday tools, organizations gain efficiencies that scale across teams. For example, a company rolling out a new internal library might use AI to generate adoption examples across multiple projects, ensuring consistency and saving developer time. These applications demonstrate that code generation is not a niche curiosity, but an emerging standard in professional software engineering. Security risks, however, cannot be overlooked. Because models learn from vast amounts of public code, they may reproduce unsafe practices such as hard-coded credentials, improper input handling, or outdated libraries. Attackers could exploit these vulnerabilities if generated code is deployed without review. The risks extend to adversarial use. Prompts could be manipulated to generate code with hidden backdoors or malicious functionality. These concerns make it clear that security must be integrated into the development workflow, not assumed by default. Static analysis, repair loops, and human oversight remain essential, ensuring that generative power does not come at the cost of safety. In industries where stakes are high, such as finance or healthcare, rigorous safeguards are especially critical. Intellectual property concerns complicate the adoption of code generation systems. Models trained on public repositories may inadvertently reproduce snippets of copyrighted or licensed code without attribution. This raises legal questions about ownership, licensing compliance, and fair use. Organizations deploying these systems must establish guidelines to ensure that outputs are reviewed for potential conflicts. Transparency about training sources and clear policies around generated code usage are increasingly necessary. Intellectual property concerns illustrate that technical capability cannot be divorced from legal and ethical frameworks. Companies must balance the benefits of automation with respect for the rights of original creators, ensuring that innovation proceeds within boundaries of fairness and compliance. Ethical implications of code generation extend beyond ownership to questions of accountability. If AI generates code that later fails, who is responsible? The developer who used it, the organization that deployed it, or the creators of the model? This ambiguity underscores the need for clear practices that emphasize human responsibility in the loop. AI is a tool, not an autonomous agent, and developers must remain accountable for verifying and validating outputs. Ethical practice also involves ensuring that code generation does not become a crutch that undermines skill development, particularly for learners. Used wisely, these systems enhance productivity and learning. Used carelessly, they risk eroding foundational understanding. Ethical adoption means balancing empowerment with responsibility, ensuring that humans remain active stewards of the code they ship. As the field evolves, it becomes evident that code generation is not an isolated achievement, but part of a continuum that connects to broader structured reasoning tasks. Just as software requires precision, so too do spreadsheets, databases, and tabular reasoning systems. The transition from generating code to reasoning about structured data illustrates a shared foundation, the ability to move from human intent to machine-precise execution. Code generation systems thus set the stage for future domains where accuracy, structure, and accountability are equally critical. The story of these systems is not only about what they create, but about how they integrate into workflows, safeguard against risks, and expand the capacity of human developers to build reliable, ethical, and innovative software. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Interactive coding assistants represent one of the most visible and widely adopted applications of code generation systems. These assistants integrate directly into the development workflow, offering context-aware suggestions as a programmer types. Unlike static autocomplete features, interactive assistants adapt dynamically to the project's libraries, coding style, and immediate context. For example, if a developer begins writing a function that queries a database, the assistant may suggest the correct SQL syntax, error handling routines, and even optimizations based on best practices. The benefit is not just speed, but reduced cognitive load, allowing developers to focus on logic rather than syntax. These assistants embody the shift from code generation as a novelty to code generation as an indispensable partner in daily work, functioning almost like a pair programmer who never tires and continuously learns from collective data. Automated documentation generation is another transformative use case. Documentation has long been one of the least favored tasks in software development, often leading to outdated or missing references that frustrate future maintainers. Code generation models can automatically draft comments, usage examples, and even high-level documentation by analyzing source code and natural language annotations. For instance, they might generate a description of a function's purpose, list its parameters, and provide a sample input and output. While this documentation may not always be perfect, it provides a valuable baseline that developers can refine, drastically reducing the time spent on routine writing. By ensuring that documentation is always at least partially present, automated generation improves software quality and maintainability, addressing a chronic weakness in the industry. Code translation showcases another capability: converting code between programming languages. Legacy systems often rely on outdated languages that are costly to maintain because fewer developers are proficient in them. Automated translation can accelerate modernization by converting codebases into contemporary languages while preserving logic. For example, COBOL or Fortran programs can be translated into Python or Java, facilitating integration with modern tools and infrastructures. Similarly, developers can prototype in a language they are comfortable with and then convert to a language required for production. This translation is not trivial, since languages differ in idioms, libraries, and paradigms, but advanced models increasingly capture these nuances. Code translation highlights how generative models can support cross-language interoperability, breaking down silos and extending the lifespan of valuable software assets. Debugging assistance reflects another frontier where generative models prove valuable. AI systems can analyze code for common patterns of bugs and propose corrections. For example, they may suggest adding error handling for file operations, correcting off-by-one errors in loops, or identifying inefficient queries in database code. Debugging models can even explain why a particular error is occurring, serving both as a repair tool and an educational guide. While not infallible, they provide a starting point that accelerates troubleshooting. By surfacing likely causes and fixes, debugging assistants reduce the time developers spend chasing errors, allowing them to resolve issues faster and with less frustration. This capability aligns with the broader vision of AI as a partner in development, not replacing human judgment, but enhancing it through rapid, context-aware insights. Workflow automation illustrates how code generation systems extend beyond snippets into broader development processes. Many programming tasks involve repetition, such as creating CRUD, create, read, update, delete operations, setting up build configurations, or wiring together APIs. AI models can automate these workflows, generating complete modules or scripts that reduce manual setup. For instance, a developer working on an e-commerce application might ask the system to generate all the scaffolding for handling product records, from database schema to REST endpoints. Automation reduces drudgery, enabling teams to allocate their attention to higher-value tasks. The result is faster project delivery and reduced likelihood of human error in repetitive work. Workflow automation demonstrates how code generation scales from micro-level assistance to macro-level productivity enhancement. Integration with integrated development environments, or IDEs, is crucial for usability. Developers work within familiar tools, and embedding AI directly into these environments ensures adoption without disrupting established workflows. When AI is accessible within the same window used for coding, debugging, and testing, it becomes a natural extension of the process rather than an external tool. Integration provides context, allowing AI to draw on the open files, project structure, and version history. This context awareness makes suggestions more accurate and relevant. IDE integration also allows developers to accept, reject, or modify suggestions seamlessly, keeping humans in control. The design principle is clear. AI must meet developers where they already work, fitting into their environment rather than requiring them to change habits. This integration is why coding assistants are increasingly viewed as standard features rather than add-ons. Customization by domain enhances the utility of generative code systems in specialized industries. General-purpose models may struggle with niche requirements, such as medical imaging software, aerospace engineering, or financial risk analysis. Fine-tuning models on domain-specific datasets improves their ability to generate relevant and accurate code. For example, a healthcare-focused model might learn the intricacies of HIPAA-compliant logging, while a finance model might specialize in secure transaction handling. Customization ensures that generative systems are not just broadly capable but deeply useful within particular contexts. Enterprises investing in domain adaptation gain competitive advantages, as their developers spend less time correcting irrelevant outputs and more time leveraging tailored insights. This adaptability highlights the importance of flexible architectures that allow organizations to align AI with their unique needs. Benchmark datasets play an essential role in evaluating and comparing the performance of code generation systems. Human eval and MBPP, mostly basic Python problems, are widely used benchmarks that test models on standardized coding challenges. These datasets provide measurable metrics for accuracy, functionality, and efficiency. Benchmarks reveal strengths and weaknesses, such as whether models handle algorithmic reasoning better than practical scripting, or whether they excel at boilerplate generation but struggle with creative problem solving. By establishing transparent baselines, benchmarks allow researchers and practitioners to track progress and set realistic expectations. They also provide a shared language for evaluating claims, ensuring that improvements are grounded in evidence rather than anecdote. Benchmarks serve as both a yardstick and a catalyst, driving the field forward through accountability and competition. The future of code generation points toward more advanced reasoning capabilities. Current systems excel at surface-level tasks like pattern completion, but often struggle with deeper architectural concerns, such as performance optimization or scalability. Future systems may integrate reasoning about trade-offs, balancing speed against memory use, or security against convenience. They may also become more adept at integrating across modules, ensuring coherence across an entire codebase rather than isolated snippets. Such advances require combining generative capabilities with symbolic reasoning and formal verification, creating systems that not only write code but reason about its implications. The vision is of assistants that understand not only how to write functions, but how those functions fit into larger software ecosystems. This would elevate AI from a code completer to a genuine collaborator in system design. Human oversight will remain indispensable, even as systems improve. AI-generated code, no matter how sophisticated, carries risks of errors, inefficiencies, or vulnerabilities. Human review ensures that outputs align with project goals, coding standards, and ethical practices. Oversight also reinforces accountability. If code fails, responsibility must lie with developers, not the model. By keeping humans in the loop, organizations maintain trust in the systems they build. Oversight does not diminish the value of AI but contextualizes it, recognizing that automation is a tool that amplifies human capacity rather than replacing it. Responsible adoption involves clear practices for validation, review, and accountability, ensuring that generative systems strengthen rather than weaken software integrity. Educational applications highlight another dimension of code generation's value. Students learning to program can use these systems to generate examples, practice problems, or explanations. For instance, a learner might ask for a function that implements bubble sort and then compare it to their own attempt. Code models can also explain errors or suggest improvements, serving as tutors that provide immediate feedback. While care must be taken to avoid over-reliance, these systems lower barriers to entry, making programming more accessible. They also allow learners to experiment safely, testing ideas without fear of breaking real systems. Education demonstrates how generative AI can broaden participation in software development, democratizing skills that were once limited to those with formal training. The impact on productivity is one of the most cited benefits of code generation systems. Developers report that AI assistants reduce time spent on repetitive tasks, accelerate onboarding for new projects, and improve overall flow. Productivity gains are not uniform. Some tasks benefit more than others, but the cumulative effect is significant. Teams can deliver projects faster, adapt to changing requirements more easily, and maintain higher morale by reducing drudgery. These improvements contribute to competitive advantages for organizations, making generative AI not just a convenience but a strategic asset. Productivity is the tangible outcome of combining generative power with human oversight, where the synergy of man and machine delivers more than either could alone. Cross-domain integration illustrates how code models interact increasingly with agents and pipelines. Instead of existing as standalone assistants, they are being woven into larger systems that combine reasoning, planning, and execution. For example, a workflow automation agent might generate code, run it, evaluate results, and refine outputs iteratively. Code models also integrate with tools for deployment, testing, and monitoring, becoming part of continuous integration and delivery pipelines. This convergence demonstrates that code generation is not just about producing text but about participating in entire software lifecycles. By linking with agents, code models extend their reach beyond development into operations, compliance, and optimization. Cross-domain integration shows how generative systems evolve from assistants into collaborators embedded in end-to-end workflows. Research directions point toward uniting generative models with formal verification. Formal methods use mathematical proofs to guarantee that code satisfies specific properties, such as safety or correctness. By integrating verification into generation, AI could produce code that is not only syntactically valid, but provably correct with respect to requirements. This would address one of the deepest limitations of current systems, their tendency to generate plausible but incorrect solutions. Combining generative flexibility with formal rigor offers the promise of systems that create reliable software at scale. Such advances would represent a paradigm shift, bringing together the creativity of statistical models and the certainty of symbolic reasoning. Research in this direction is still nascent, but holds immense potential for industries where correctness and safety are non-negotiable. As code generation systems evolve, their trajectory naturally connects to other structured reasoning domains. Spreadsheets, databases, and tabular systems share the need for precision, accountability, and reliability. Just as code requires syntactic accuracy, tables require structural coherence, and queries require logical precision. Code models pave the way for systems that reason across these domains, integrating programming with data manipulation and analysis. This convergence highlights a broader principle. AI is moving steadily toward mastery of structured reasoning tasks that amplify human decision-making. By building trust in code generation, society lays the foundation for adopting AI across equally critical domains where precision and accountability matter just as much as creativity. Code generation systems, therefore, represent both a powerful tool and a responsibility. They accelerate development, automate routine tasks, and support learners, but they also demand oversight, security, and ethical care. Their future will likely involve deeper integration with reasoning systems, formal verification, and cross-domain applications. Used wisely, they empower developers and broaden participation in software creation. Used carelessly, they risk introducing vulnerabilities or eroding accountability. The balance lies in combining automation with human responsibility, ensuring that code generation systems become trusted collaborators rather than unchecked authors. As organizations and individuals navigate this balance, code generation will become an integral part of how software is conceived, built, and maintained in the decades to come. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.